scientifically designed, maintained in a clean fashion, and fit properly. One of the most common yet overlooked pieces of personal protective equipment is the hard hat. Today we are going to test the importance of our ANSI Z89.1 Type 1 Class E Sans hard hat on our volunteer melons. 4 objects commonly found out in the field, each of varying weights, will be dropped from 20 feet, both with and without the proper protective equipment. We will begin with a washer, weighing less than a pound. Falling at a speed of 25 miles per hour, this washer will have an impact of approximately 61 pounds of force.
3, 2, 1.
As you can see, Mel made it out safe.
Now without the hard hat.
3, 2, 1. Oh. Gross. That is a legit washer too, huh?
With this light little washer, Mel's not feeling too good after that one.
The next object to be dropped is a 3/4 by 22 inch machine bolt, weighing 2 pounds. This will have an approximate impact of 122 pounds of force on the melon.
3, 2, 1. A little scratch, a little nicks from the thread. Pretty unscathed under the net.
Now without the Sans hard hat.
3, 2, 1. Oof. Not a good day. That baby went all the way through. I got hit by a 1 volt once, right on my collarbone point. It was bad. So the bolt, without the hard hat, went all the way through the melon, or the head. It's gonna be tough to let this one go, guys.
Next, a 3.5 pound hoist handle will be dropped, creating up to 213 pounds of impact on our unsuspecting melon.
3, 2, 1. Skimmed a little bit. Still survived. Scuffed up her forehead a little bit, but you're gonna get that. That's not too bad though.
Again, but this time without our hard hat.
3, 2, 1. That hoist handle didn't do Sweetie no good. I think she's allergic. It went through above the right eye, all the way through, and it probably would have poked all the way through, but it hit the collar there. Some Humpty Dumpty stuff right there.
The final object is a pull-top pin with insulator installed, weighing approximately 8 pounds. This should create up to 488 pounds of force.
Tighter so suspension's working. And 3, 2, 1. Oh, that makes my neck hurt.
It was a direct hit right on the top. All we have is one little mark on a rib. It was hard enough, the collar pushed on the bottom. Everything looks good.
And finally, without our hard hat.
Okay, and 3, 2, 1. Oh, man. I'm gonna eat that.
It stopped on the collar. It probably would have went all the way through.
That's impressive. That'll make you a believer in a hard hat. You want some watermelon? No. Why not?
The effects of a hard hat are obvious, but one's personal protective equipment should be the last line of defense. Safety requirements may seem inconvenient at the time, but in the end, it could save your melon. Don't forget the importance of your PPE.
And remember, safety is so sweet. Look at all this land out here. We don't have our own watermelon patch.
Okay. Any comments there, Mr. Tanner?
Yeah, wear your hard hat.
Yeah, insane the membrane. Insane the brain. Is anybody right there at the beginning of the video? PK got the OSHA specification for what type of hard hat you're supposed to have. Does anybody remember what those numbers were? Letters and numbers?
Personal protective equipment, commonly referred to as PPE, is specific equipment worn to minimize hazards in the workplace. These injuries may result from contact with chemical, physical, electrical, mechanical, and other workplace hazards. In order to get the full use out of your PPE, the equipment should be safely designed, maintained in a clean fashion, and fit properly. One of the most common yet overlooked pieces of personal protective equipment is the hard hat. Today we are going to test the importance of our ANSI Z89.1.
Okay. ANSI, what?
Z89.1.
Z89.1. Fantastic. Great answer right there. All of the safety and personal protective equipment that you're going to be looking at right there, as far as hard hats and safety glasses, are going to be classified in two areas: Z87.1 and Z89.1. The difference between the two: Z87.1 is impact resistant. Z89.1 is impact and electrical resistant to the specification of whatever you're using right there. So if you're working in the utility industry, what kind of hard hat do you want to have, a Z87 or a Z89?
89.
89, absolutely. And how about your safety glasses? 87 or 89?
89.
All right. Z87 is good enough. The utilities don't, they don't expect you to stick your eyes into a energized power line. Z87 is acceptable, so you don't have anything that impacts or goes into your eye. But Z89 does give you the electrical protection. So a Z89 hard hat requirement. Z87 is the minimum requirement for safety glasses. Now there's and this is kind of I'll share my screen right here. As far as Safety Cooper is concerned, there's a problem with this hard hat. What is it?
They don't go all the way around?
No, has nothing to do with the design of the hard hat. That is acceptable. They do make hard hats that have that a longer bill in the back and more of a broader, longer bill in the front. That's the kind I usually like. One, it keeps the sun off you. Mm-hmm. Two is, you got more protective area right there. There's something on the hard hat that's really not supposed to be there.
The things on the side.
The things on the side, that's where you put your goggles at here. You see this thing right here?
The manufacturer.
Yeah. As far as a Z89.1 hard hat, there are supposed to be no stickers or no painting of any kind on the hard hat. Once you include something like this on the hard hat, especially if you put it on yourself, you have degraded the insulation quality. A sticker is not insulated. The hard hat is. So don't add stickers or paintings or other cool stuff to your hard hat if it's a Z89 1.1 hard hat that's supposed to be an insulated property. Now, this thing looks pretty brand new, right?
Yep.
Yeah, it looks like it's fresh out of the box to me.
Yep.
Keep your hard hat clean. Keep the liner clean. That does have an influence on the electrical insulation properties of a Z89.1 hard hat. All right, any other questions on hard hats? One thing you will notice in the videos, and I kind of like that video, it's a pretty good one, Tanner, is a hard hat will not stop injury. If you'll notice, most of the ones where they were dropping something on the plain watermelon, it impacted into the watermelon. A hard hat is meant to deflect objects that come down. So if it hits here, it's going to deflect, and the energy is going to go down to the ground. Whereas something banging on your skull is going to just bang full force on your skull. And people get the assumption, well, I've got my hard hat on, Now I can walk under a 500-pound switch. You know, no. Always keep aware of what's above you. It's meant for little things like a staple or a nail or something like that that gets away from you. And once again, you got a hard hat on and somebody else headache, what do?
Run away.
Run away. Don't look up and take one to the grill. Okay, that's most people's first intention. Headache, and the first thing you do is look up to see what's falling. Don't do that. Move away from the pole.
Type 1, Class E.
All right, good deal. Any other comments on the hard hat video from anybody?
Wear them.
Say again?
Wear them.
Wear them. That's the dang truth. Wear them. Okay, just give a little administrative stuff going on here. And I've got, is William Kennedy in here?
Cole.
Cole Kennedy?
Yes, sir.
All right. So you guys, it's the reason why I opened up the room at 8:30 and class starts at 9 is for you to have the opportunity to work out any kind of malfunctions or to text me and let me know if anything is going on so you're able to make attendance in class. Cole Kennedy used his big old noodle right there this morning, got into the class, he texted me, Zoom kicked me out, and you know what? That's okay. He made attendance. For you guys that are showing up at 9:01, 9:02, 9:05 for the first time, that's tardy.
Tardy.
3 tardies equals an absence. 3 absence equals a drop of the class. If you're having technical difficulties and can't get in, text me. You also have 30 minutes prior to class to log in. Even if you log in and go do like Tanner does, fix your bowl of Cheerios or Cocoa Puffs, get logged in. Any questions there? All right, there will be a quiz today. We're gonna go ahead and do some more math this morning. We're gonna go out to the field this afternoon. I got a 10 question quiz. I'll go ahead and review it with you right now so we can take a look at it and you'll get an idea of what the questions are so you're able to study for it. And let me get back to it. So we will post this in D2L. All right, and it's 10 questions. You don't have to shout out any answers right here. This will be on video too, so you can see it later on. The questions comprise of question 1. You should have a screen up right here of me sharing it.
Yep.
What does, for lineman, the definition KVA stand for? What does impedance mean? I'm going to do a little math here. A 25 kVA has an impedance of 2.6%. What is the true kVA? Make sure you put it down in kVA. Define volts, define amps, define watts. Remember, I like
choice.
Huh?
Is this multiple choice?
Yes, all of them multiple choice. See that MC?
Good.
All multiple choice. Define volts, define amps, define watts, and you'll notice in my answers right there that I've given for the multiple choices, it's short and simple. What can a transformer be overloaded to for a short time in percentage? I'm not giving you the transformer. I want to know the percentage number that a transformer could be overloaded to. A 25 kVA. I don't know if this will show the answer or not. I hope not. Oh, yeah, it does. A 25 kVA transformer could be overloaded to what kVA? So give me the next kVA. A 50 kVA transformer is overloaded to 150% and has an impedance. I know what that is over there. So you're going to have to overload it to 150% and then calculate the impedance to give me the final kVA. So I'm doing, what I'm doing right here is I'm doing an impedance and an overload all in one question. All right, and the last one, and we can all shout out on this one right here. When pulling poles, you may stand between the pole and the truck. True or false?
False.
False. Do not get in between a pole when pulling it and in the truck. So you've already got one answered right there. What is the total of 91? Why is that going on?
Number 4.
Number 4, I've got to change. So you got to change it too, V.
Yeah.
All right.
When is this available, sir?
When is this available? After lunch.
No. Okay. I may have to do it while I'm at school on site because I work right after the class and then I don't get home until 12:30 in the morning.
Ooh.
All right. Well, let me unshare here. Give us a moment. Who else is working tonight late?
That's the same thing.
I don't get out till 12.
Okay. V, go ahead.
I go
V.
straight to work after school and don't get out till
All right.
12 o'clock, 1 o'clock.
All right. You guys take a break. What time is it? I know it's kind of weird to take a break right after a safety meeting. It's 9:30. How about give us till 9:45? We'll go ahead and make it available right now.
Awesome.
All right.
Appreciate it.
Yep. Stand by. I'm going to go ahead and go to edit here,
Okay.
Rob.
Right on. Edit. And number 4. Come on. Come on. Close.
So number 4, we need to change to 10. Save. Got 100 points. Restrictions. Unhide it. Has a start date of right now. Has an end date of midnight tonight. Display calendar. Okay, so Robbie, I changed number 4 to 10 points.
You did. Correct.
I went to restrictions and took off the hide. Has a start date of 9/1, has an end date of 9/1
Right.
at midnight, and display calendar.
Yep.
All right, save the class. So I will be okay. I'm back. It's 9:45. Couple more things to ask, and then we'll get started back on the math portion of this morning. Everybody in the room here, I'm sorry for the lateness last night, but I texted everybody Mark Jones's email. If you have not, again, if you have not received an invoice or an email from Mark Jones yet, please tell me who you are. Tanner Carpenter. Tanner.
Sir.
All right, did you hear my question?
No, sir.
Did you hear my question?
No, sir.
Okay. Have you received an email from Mark Jones yet?
Oh yes, sir. I called him yesterday, and he wrote down my email wrong.
Okay.
But
That's fine.
yesterday.
Cool. All right. So we got that squared away. Everybody else here in the room, anybody else who has not received an email for an invoice from Mark Jones? Okay. I'll probably text that out too to make sure everybody gets that information. Once again, gentlemen, I will advise you here, now that you've got your invoice, don't sit on it. I mean, if you got changes you need to make them now. I would suppose that even at that, they would probably be very minimal. Who's that?
Caleb.
All right. Make sure Caleb, I'll ask Caleb this question. Hey, Caleb.
He's coming.
Caleb Cook.
Radcliffe.
Oh, Radcliffe? Radcliffe. I'll just go through everybody when we get out to the field this afternoon.
Yeah, just says he's joining.
Okay. Is now that you received your invoice, you've got to reply back to him and let him know that you're okay with the invoice. You don't have to pay now. Just let him. Why does everybody leave and then come back? Just let him know that you're fine with the invoice and go with it. Otherwise, he will sit on it until you approve. And as 33 people that we have in the class here, the faster everybody gets it done, the faster we get our tools delivered to us. One person holds up everybody. He does everything in a batch right there in order to keep everything really square. He does cater to 4 other colleges, so he's pretty hammered, plus all the regular business that he has out there in the world. Let's make it as easy as possible on him. And when we do that also, it really minimizes errors, both on our side and his side. Anything you want to add with that, Professor V?
No, just don't hold nobody up.
Yeah.
Get it done.
Okay. All right, so let's get back into the math books. I have moved up to, sorry about that. Hope everything comes out all right. Gee, that was kind of harsh.
Yeah.
Average and estimates. I'm in Unit 20, page 98. Now, we'll let you know, as far as the industry is concerned, they're really not going into doing very many estimates. You don't want to really estimate anything. You want to give true numbers of what's going on. Now, there's a little bit of rounding that may go on in numbers or whatnot out there in the world, but not really estimating. Especially, and I'll go back to this one yesterday, we talked about percentages for a little bit. Let me bring up another screen here and I'll just give you an example of what you may run into. Get this all squared away. Get the coffee moved. Okay. Okay, you should have one of my share screens up again of just a plain paint. Okay. So what happens out there as far as you guys getting your jobs and whatnot early in the morning, and an engineer will draw up your work for the day, and either a person on your crew or a coordinator in your area that you're working at will assign that work to you. And you typically is the first brand new guy on the crew. The first couple weeks, probably about the first month or so, somebody's going to go in with you, and you're going to have to pick up material off the yard, like cable and transformers and pipe and all kinds of different stuff. And then some stuff's going to have to be delivered out of the warehouse. That's in the warehouse on a buggy usually, and then you're going to stock your truck up with it. Well, here's what some, not all, some engineers do. Let's go to this. They'll go out on the initial look at the job site and say, I have a pole here, and I'm building a new house over here. Okay, and here's my meter, where my meter is going on the house right here. And what they'll do is they'll take steps And the typical gait of a person is 3 feet. So as soon as I take a normal step, it's 3 feet. So if I walk 20 steps from this pole to this house, how many feet is that?
60.
60. Okay. 60 feet. And that's what he'll put down on the work request. You need 60 feet of cable to reach from the pole to the meter base. How much wire do you need?
More than 60 feet.
More than 60
70.
feet. Very good. Very good. You need more than 60 feet. And the general rule out there in the world is add 10%. So if the guy says you need 60 feet,
60.
take 70, maybe even 80, because you're going to have a little bit of extra to connect here. And you're going to need a little bit of extra to connect to your transformer up here. So never, ever go to a job site with the exact number even a good engineer puts on a work request. Now, a good engineer, and not to say that, well, I'm going to go ahead and say it. There are some good ones, there are some bad ones. A good engineer is going to say, I walked off 60 feet. I'm going to give them 75 on the ticket. I'm going to tell them to bring 75 feet. If they tell you to bring 75, how many feet are you going to take?
90.
90. There you go. Great, great, great answer. Take 90. They're not really, and Professor V, you could probably come in on this too.
Yep.
They're not really overly concerned with you scrapping wire. Now, you get into the 20s, 30s, 40s, 50s, 100s feet of wire to scrap, throw in the trash bin. They're going to kind of scratch their head a little bit and say, hey man, you're wasting wire. But as
Yep.
far as the, the short pieces that you're using, they're okay with that. How about you? How about Duke Energy?
That's correct. These short services, we always carry coils of wire on the truck, and it was always better to have too much than not enough, because you really didn't want to put any splices in the wire to start with in any kind of new service. So
Absolutely.
always give a little bit extra.
Yep, yep. I think another big one that we saw out there with some engineers is, I've got wire that comes down a pole. And here's ground level. Wow, my ground's lumpy. And I'm going to a transformer that sits on the ground. So you got to come from the top of the pole, down 4 feet, over here, up 4 feet, and even with a wheel, they will wheel off from here to here, and they will tell you, how much do you need? 100 feet. All right. This is one to especially look at. And if they're telling you 100 feet, do you need 10% more, or do you need even more than 10%?
Need more than that.
Yeah, yeah. I would go ahead and carry 150 to maybe 200 feet with this, because I'm going up a 40-foot pole. That's 40 feet right there. I'm going down 4 feet. So we'll add them. 40, 4, 4. That's 8 feet. Well, there you go. 148 feet. I need to terminate in here. A little bit extra coming out of the ground. So carry extra. As far as, you working on a job and you coming into an organization, your fellow linemen on the crew are going to teach you this and give you this information. It's good to know right ahead of time. The thing is, you don't want to, if you learn that information, you don't want to be caught short-handed, even when you've got something that's really not needed on your truck for the day. A flatbed truck or a material truck, even a bucket truck or a line truck, is just going to have some spare material. They're going to have a couple extra switches on a truck, some extra bolts, nuts, washers. It's just going to ride around with you all the time. Make sure that those things are stocked on your truck. But when it comes to wire especially, make sure you've got more than enough. You got that, B? Thank you. Make sure that you got more than enough. I've seen actually sometimes where the case was, well, I need 100 feet. You don't need to go out in the yard and cut 100 feet of conductor off a reel. Take the whole reel.
Take it all.
Yeah, take it all. And once you pulled off that wire on the job site and used what you needed, deliver the reel of wire back. That's probably the best way. I know, and I'll give you an example of myself. When I first started working with Santee Cooper, once again, we wasn't Debadoo. We went down to Hobcaw. It's even further south of Debadoo. I was at the service center loading up material, and the boss called me up and he says, I need you to load 200 feet of one URD primary. And I know you don't know what that is, but I knew what it was at the time. So I run down to the yard, I get a reel of wire, I start pulling it off, I wheel off 200 feet, put it on the truck, and I started heading down to Hopkoff on my flatbed truck. Got down to Hopkoff, and we start pushing the wire in and came up about 2 feet short. Who's at fault, the supervisor or you?
Yeah.
You are. Okay. Get that extra little bit. So you know what they did with me?
They fired you.
No, they didn't fire me, but they sure taught me a lesson. I don't know if you've been down on Hopkoff Barony, but it's deep in the woods. I had to walk to Highway 17 down there in Georgetown. I hitchhiked from Georgetown to Myrtle Beach. I got the wire in Myrtle Beach, and I had to hitchhike and get my way back down there to Hopkoff to get the wire down there to Hopkoff. Took the better portion of the day and a lot of walking. Do you think I ever did that again?
Negative.
Nope, didn't happen again. Okay, so now I'll go ahead and stop that share. Now you know, have plenty, have enough when you're leaving the service center, and that 10% rule there is a good one to remember. All right, stop share. All right, back to the booklet. Average and estimates. How do we figure out averages? Simple enough. If you've got, I'm looking at example 1 there. I'm looking in the book, it's showing dollar amounts of 68.50, 87.34, 103.09, and 77.16. All you have to do is add all the numbers together and divide by the amount of numbers that you have. So they're including 68.50, 87.34, 103.09, 77.16. So the addition of all those and divide by 1, 2, 3, 4. That'll give you an average. So the addition of all those is 336.09. Those numbers added together and they divided by 4. So your average cost is $84.02. Has anybody got any question on averages? I'm not going to get into that too much. It's not done very much out there in the world. If I got 84, let's change that to feet. If I've got 84 feet that I need to get, how many feet am I going to take?
100.
Go ahead and make it 100. It's more than 10%, but it's a nice round number. What's going to help you too, guys, let me bring up a picture right here. Let's go to images. Oh yeah, that's a perfect one. And this applies to all conductor nowadays that's coming out there in the world for utility use. Let's see, share screen, first screen, share. This is a reel of underground primary. I don't like the way they got this one right here, the way they're showing it. First, it's going to show you the wire size, the voltage rating on it right here. I don't know if there's going to show in this area, but it is stamped on it. There's footage marks on the wire. That's for all conductor except for bare conductor. You can't put a footage mark on that. All covered or insulated conductors got a footage mark on it, so you're able to tell how many feet that you're pulling out.
Is that 175? That's not 175 miles, is it?
Mils. Mils is the
Millimeters.
thickness of the cable.
Right.
Okay. No, not 175 miles. Professor V, you could probably chime in on this too. Because of overhead conducting, when you start getting in, and this is pretty, decent sized wire right here. You're going to try to get for delivery and for the reels to match your trailers and whatnot, you're going to get conductor in increments of miles and dividers of that. So typically on a reel of this kind of conductor, you're going to get half a mile. On a conductor of overhead, probably of a smaller size, you're going to get a mile. Some bigger conductor, you're going to get a quarter mile. It's made like that for two reasons. One, you want the reel to fit your trailer. And two, is just better to use in those increments, especially when you're building long lines. You know how much to carry with you.
Right.
And it's easier to engineer.
Yep.
Anything you want to add there, Professor V?
No, sir.
Okay. You'll notice, and just because we're sitting on it right here, what year is this conductor?
2006.
2006. They've upgraded this type of conductor right here. It's underground primary conductor, and it now includes a red stripe. This voltage symbol has gone away, and now it includes a red stripe, so people can recognize, in case they dig down, that this is a underground power cable. People have mistaken this in the dirt for water line, and taken hand cutters and whatnot, or just regular cutters or a sawzall and whatnot, and thinking they can cut a water line out of the way when it's actually got, what size is this? Yeah, 15,000 volts on it. Okay, so back to math. Math. All right, so that, once again, we're not going to go through estimates. The Unit 21 combined problems on percents, averages, and estimates. Well, we know percents and averages. Not really worried about combined operations. We are going through this book. Okay. Unit 22, powers and roots. I'm on page 106. How do you compute a power? Anybody? If anybody has their book, what are they doing on the example on page 106?
Raising 6 to a 5th power. So you multiply the main number by the
amount of the power. Is that what you're saying?
The example is showing the main number, the 6, is multiplied 5 times.
Okay, yeah, you're using the bottom one down there.
Yeah.
Whatever you have in a power, when you're working with powers, if I've got 5, to the power of 2, whatever you have for the main number, multiply it by the amount of powers that you have. 5 times 5. 5 2 times equals 25. The next one down there, 8 to the power of 3 is 8 times 8 times 8 when you punch it in your calculator, which gives you a total. 8 times 8 is 64. 64 times 8 is 512. All right, and last but not least, what Mr. Paul was talking about is 6 to the power of 5. Six to the power of 5, 6 times 6 times 6 times 6, 1, 2, 3, 4 times 6 equals 7,776. Yes. Okay. Any questions there? Good deal. All right. Skipping through. Just as long as you know powers. All right, roots. So how do you compute a root of a number? You're just really going into the opposite direction of what you did in powers. A root cannot include a fraction. So it must be divided by the same number to itself. If I want to give an explanation to that, the simple one that's in the example, find the square root of 100.
10.
Right, 10. How many times?
10.
Times 10. You've got to have the same number here and here. These cannot be a combination of 2 and 50, or give me another 4 times 25. These two have to be the same number to be computed to be the square root of the number that you got asked right here. So this is a simple function on your calculators. If you punch a number in and hit the square root key, it's going to give you the answer right away. So that's how you compute a square root. Any questions on square roots? It's quiet in the jungle today, isn't it, Vic?
Yes, sir. Yes, sir.
All right, don't say it.
We're doing cube root as well, or just square roots?
Say again?
Will we be doing cubed roots or just square roots?
Cubed roots? I hope not. I don't think there's any need to do cubed roots in the Lyman world.
Right.
Okay. All right, so I've moved up, and like I say, you know, we're going to breeze through this and make it for a lineman, not for an electrician in this book. I have gone up to 121, metric, measure, and scientific notation. Notation. And I will let you know the ones that you need to know out there in the world, and keep these in your notes. I'm actually going to go ahead and turn to page 122. All right. In the industry, you really don't need to know about tera or giga. You will need to know mega. Mega equals what?
10 to the 6th, I believe.
Go ahead and just, I like the word. Million. All right. What's kilo?
10 to the 3rd.
I like the word.
1,000.
1,000. Excellent. Base unit, and really, I mean, you may run into the situation if you go overseas that you may see the giga out there in the industry, but it's going to be rare. The milli, micro, nano, and pico are not used in the utility industry. I got them. Are not used in the utility industry. So let's go talk about a couple of things here. Get our definitions right. File, new, don't say. All right, I'm going to pop these out there. 1 kV, 1 kilovolt. How many volts is that?
1,000.
1,000 volts. 1 MV equals
1,000,000 volt.
1 million volts. 1, 2, 3. I forgot a 0 there. 1, 2, 3, 4, 5, 6 volts. All right. And 1 GV.
Billion.
All right, 1 billion volts. Okay. File. New. Now this applies to all two, and I'll put up the symbology here. What's V stand out there in the world for us? What does it mean for us?
Volts.
Volts. What is A?
Amps.
Amps. What is W?
Watts.
Watts. Thank you very much. So whatever combo that I use as far as the giga, mega, and kilo, as soon as I put this letter after it, is the designation of what it's for. 1 kV, 1 kilovolts. 1 MA, 1 mega amp. 50 kW, 50 kilowatts. Now we've been talking before, and this gets just a touch into Ohm's law. I don't want to go too far on that yet. We have talked before when we've seen transformers that we've seen what? 50 kVA, right? Loosely translated for us as a lineman means what? 50,000 watts. The technical term for kVA is kilovolt, and you notice I put a slash in there, amperes. All right, if you were to go to Ohm's law and look for watts, the calculation is going to be the volts times the amps. Instead of putting this all on the front of the transformer, they just convert that to kVA. And that solution is actually going to be 50,000 watts. Whoops, 50,000 watts. Okay. Yeah. Don't say. So guys, when I say, and we talked about this the other day, when I say 25 kVA, how many watts or how many, I want to say homes or places like that, it's kind of hard to tell. How many watts is that transformer able to feed at 100%?
25,000.
25,000. So that's, just keep definition of that term. If I need to feed, let's see, if it goes to an overload, if I need to feed overload for a short amount of time, what will a 25 kVA, how many watts will I get out of that transformer for a short amount of time? First, what's the overload percentage?
150%.
150%, right. Now, if I've got 25 kVA, that's normally, that's the 100%. That's what it does 100 at 100%. If I need to go to overload, I can add 12.5 to that. This is my mind working. So that's a 37.5 kW, kilowatts. All right. You know, I kind of emphasize these a number of amount of times because really the importance of these calculations can really save your day. And once again, it bounces back to what organization you're going to be working for. And to be totally honest with you, I'm sure Professor V has been in this situation. Mm-hmm. You get out here in a nice, good, hot summer day and the heat's bearing down. I'll just throw out this question. How many dispatchers do you think are working at Santee Cooper today?
Two.
There are 2 dispatchers controlling 1, 2, 3, 4, 5 areas, including Berkeley County. And they're busy. So especially on a hot day when things start going wrong and you got thunderstorms, they start getting busy. And it just, not only does it make you look good and people are going to say, hey man, that guy's got his head on his shoulders as far as getting stuff done and doing things, is when you call the dispatcher up and say, I've got a 25 kVA transformer here. How many watts will it do? They really kind of going to push you to the back. That's something you should know. And I mean, it's on a calm day when nothing's happening, they're going to say, hey man, 37.5 kW. But really, not to say that you're going to look like a dummy out there, that's something that you should really have in your brain and know already. And people are going to be questioning, hey, where did that guy graduate from? Not Professor Shoemaker's class, that's for sure. Okay. File, new, and save. Okay. So those are the ones you're going to need to know out of the book. Giga, mega, kilo. What time is it, Professor V?
10:15.
10:15. So we've been going, what, about half an hour?
Yep.
All right. I'm going to go through this without really throwing anything up on the screen because I would think I'm on now Unit 26, page 130. How many inches are in a foot?
12.
12, how many feet in a yard?
3.5.
All right. How much?
3.
3. You working metrics out there, Paul?
Sorry, from another country, brother. Sorry.
It's okay. That's okay. 3 feet in a yard. All right,
No.
I'm not worried about a mile in yards. You're not going to need to know that. But this is a number you will need to keep in your heads all the time. How many feet are there in a mile?
50.
5,280.
5,280, gentlemen. When you go in some jobs, when they're doing long, new construction or a long distance reconductoring, they're going to do that in hopefully mile sections. So say I've got to build a new line from Conway to Loris, and that's, golly, what is that? You're looking at what, 12 miles, 12, 13 miles? All right, the footage on the reel is going to come in feet. All right, and you're going to hopefully get around 5,280 feet on the reel. Well, what does that tell you right there?
12 reels. More than 12.
Small reels? Of a mile of conductor, they get to be pretty big. All right, the engineer is going to design it to where he goes from pole to pole to pole to pole to pole to pole for that 5,280 feet. And you're going to reconduct this all at one time. You're not going to come in here, pull 500 feet, put a splice in it. Pull another 1,000 feet, put a splice in it. Pull another 2,000 feet, put a splice in it. That's not the way they operate. They want to pull this full distance, 5,280 feet, when you pull the new conductor in and not have any splices in it. As soon as you introduce a splice into a conductor, you have poor resistance. I mean, high resistance and poor conductivity in that conductor. So you want to know this number. I want to pull the full distance of 5,280 feet, especially if you walk out into this job and they've designed it in this fashion. How many feet do you really want on the reel? Do you want the exact 5,280?
Probably about 5,500.
55, 56, somewhere in that area, because it's, some of it's going to, well, it's going to happen to exactly where I showed this picture right here. And you'd be
Doesn't the
surprised.
wire have sag in it too?
Yeah, you'd be very surprised how much distance is lost. And I'm going to just draw one span right here, pole to pole, straight line. And that's not really that straight. And then actual belly, what they call belly and sag. How much distance of the conductor is lost in here as far as ground distance or air distance in a straight line. So you're going to have some extra. All right. New. Let's see. All right. Metric length and measure. Paul, hate to say it, buddy, but they don't use it over here. All right.
Oh, goodness.
All right. In English, metric equivalence, length and measure, it doesn't happen over here.
Have you ever worked? This is a side question. Have you ever worked in another country and done?
I've worked in China twice.
Yeah. Is it the
Yep.
same method?
It is the same method as far as feet. No, they're metric.
Okay. It's the same method as install.
Yeah. To be totally honest with you, they're a poor third world country. Their practices, and that's really the reason why I went over there those 2 times, were to, one, teach safety, and the other was construction methods out there, because these guys are climbing poles with ladders and bamboo and bare feet.
Yeah, man. Great.
You know, was to give them some insight of how to construct and be safe. You'd be amazed at the surprising things. If you ever get, well, I mean, hold on a second. If you ever get the chance to look at some pictures, whatnot.
I would assume they don't have an abundance of pine growing over there.
They don't. They usually mostly concrete.
Wow.
And steel.
Yep.
Let me see. That's really not a good indication of it. Yeah, here's one. Hold on. They're really kind of haphazard as to their construction techniques. I'll see if I can slide this over. Woo! And that's really, for them, that's kind of clean. I've seen them worse over there. But they will, here's your primary conductors on top. They got a light on this. And they'll do what they call bulk transformation. So somewhere they'll have a huge transformer mounted up on a pole. And these are communication and secondary lines. Now, as soon as all of this is installed, I know we have linemen here and electricians in the United States. That line is kind of gray when you go to China and some third world countries out there. It was nothing for us to see a homeowner grab his ladder, throw it up at a pole, take a piece of wire, tie it in with some eye nuts up here on the secondary lines, and have power to his house. And that was just, you know, a regular Joe Blow guy. So it's really kind of messy. If you want to go, and I've been with my wife to India a couple times, you want to see where it starts getting real nasty. Is travel to India. Yeah, that's How'd you like to work on that?
Need to cut them vines.
Those are wires. And really, I mean, what's happening right here is people are just going up with some 10-2 or 12-4, whatever they've got, putting a knife to it, skinning the wire, and just, you know, twisting it together. That's how they do it.
Wow.
Yep. I mean, they'll send their kids up there to do it. Okay, so back to the book. So in measurement, know what 12 inches is, 3 feet, 1 mile. We're not going to go into doing measurements of all that other stuff. I'm up to page unit 27, area of measure. As soon as we get done with the area of measure, we'll take a little break here. Do you know how many square inches are in a square foot? $12 times 12?
Oh,
144.
144, okay. How many square feet? Let me scroll up. Let's see right here. And how many square feet in a yard?
Nine.
9 square feet in a yard. Well, you know, I'm going to go to trusty Google. How many square feet in a square yard? 9, right? And you just took 3, right? Square foot, 3 times 3 side by side equals 9. That equals 1 square yard. It depends on who you go to work for. Professor V's probably done this a couple times. You're going to have to pour some concrete sometimes. Rare, but not unknown. Okay. All right, so with that, let's go ahead and take a break. We'll give you, it is 10:26 now. Let's say 10:40. We will be back. Go get yourself something to drink. And Tanner, keep your shirt on, okay?
Always keep my shirt on.
Oh, wow. There. Okay. So let's go ahead and get us a picture of a transformer going on right here. And we'll use a pole mount transformer. It's a little refresher. Images. This is that's the one we were looking for the other day.
Yep.
With the drawings on it, and whatnot. I don't like that one. This is the one we used before. Okay. All right. So we have our transformer picture up here. Get smaller a little bit. And again, just a little refresher right here. What bushings do we use for the primary input from our primary line? Where's the high voltage come in?
The ones on the top.
One's on the top. Now, you'll see different types of transformer that only have a single bushing and don't have this bushing on the other side. Professor V jumped in on this one too.
Yeah.
This is what Santee Cooper buys. It just depends on your organization of what type transformer model that you buy. But all of them will have a what they call a high side bushing, primary bushing, and all of them will have a secondary bushing. You'll see that there's porcelain right here. It's much, much smaller, and that'll tell you what your low voltage is. Excuse me, that'll tell you what your low voltage bushing is in the transformer itself. Professor V, have you seen some single post type?
Yeah, that's mainly what Duke uses, single post on like residential voltage. We use the 2 bushing conventionals on when you start banking transformers.
Okay. The reason why, and I'm sure that you've got a good reason why that you purchased that way for Duke. The reason why Santee Cooper purchases in this way is if I want to hang a switch, you see my mouse cursor over here, and then come down with my primary feed this side, you're good to go. If I need to hang a switch over in this location and come down with my primary feed on this side, you're good to go. So either bushing is kind of usable depending on where you want to put your switch. So it gives you just a little bit more options. Now, I do know for a fact that single bushing transformer does cost less than a double bushing one does, but they both serve the same purpose. Primary input, secondary output of a transformer. Any questions there? All right. Which one is the neutral bushing? Or where does the neutral ground line go into?
In the center.
In the center, and it's easily identifiable by that ground strap that you see right here. We'll say for this transformer's sake, I don't see the nameplate, that we have 7,200 volts coming in, and this is for a residence. So how much voltage do we get out of this?
120,
120 and
240.
120, each one individually.
120.
120, and the combination of the two,
240.
240. Okay, excellent. So now actually when we're given these voltages right here, we now have a ratio, and we're working on it right here. We're going to deviate a little bit in the book for you to be able to do calculations as far as volts and amps and watts. They narrow it down to, it's got to be a non-fraction number. So I'll give you an example of the picture, the one that we have right here. File, new, don't save. And do my drawing a little bit better here. Let me get this pad over. So I'm going to draw that same transformer out. Probably not as good. All right, and here's my secondary bushings, 1, 2, and 3. When you're doing ratios on transformers, you want to use the total input voltage and the total output voltage. which we have already determined. How many volts did we say that were coming in?
7,200.
7,200 volts. How much voltage do we say was coming out?
2,400. 240.
240, thank you. Use the total number right here. 7,200 V, 240 V. Now we're going to figure the ratio, and this is really simple to do. Take your 7,200 and divide it by 240. Anybody?
30. 30.
What was that, Paul?
30.
30, okay? 30 is our solution. Now, here's the big thing. I got to know where I need to put this. Does anybody have an idea? Does it go 1 to 30? Or does it go 30 to 1?
It goes 30 to 1 because it's a reduction.
Careful now. And here's the easy solution that I could find to fix that. What's 30 times 7,200 times 200 and, yeah, it's huge, right?
Yeah.
21,600. Is that the same number that I have down here?
That's 210,000, 6,000.
Right, it is not. What's 30 times 240?
7,200.
7,200. So that is my ratio. For every one of these, I need 30 of these. 30 times 240 is 7,200. So that's your ratio of the transformer. It's a 1 to 30 ratio with these voltages that I have provided. Is everybody tracking there?
Yes.
All right. File, new. Don't save. And when Professor V and I give these voltages, these are actual system voltages. All right. So new transformer, and I'll let you guys figure this one. One, two, three. Input voltage 19,900 V. Output voltage 240 V. What is the ratio? Somebody talk me through the math.
I got a quick question.
Yes, sir.
Is that 19,900?
Correct.
Okay.
Talk me through the math. What are you doing?
19,900 divided by 240.
Thank you. 19,900. I'm going to divide that by 240. What is your solution?
83.3 if you round.
93 point what?
83.3 if you round up.
83.3 if you round up. I'm okay with that to the, what is that, the 10th.
Yeah.
So, and here's the easy way to remember it. If I take 83.3 and multiply it by 240, I should be at that number, correct?
Yes.
All right. So where does the 1 go?
Up top.
There you go. It's 1 to 83.3 in the ratio of this transformer. There are multiple voltages. Professor V?
Yep.
Probably a good thing we need to do this afternoon or tomorrow is go ahead and post that sheet of the common voltages.
I printed it up yesterday. I'll hand it out this afternoon.
Excellent, excellent. Professor V is going to hand out the common voltages on distribution systems. We're going to go through a couple more of these here on paper just so you guys get the concept.
Hey, I got a different number than that.
You got a different number? I'm not using a calculator, so do please let me know. What's 19?
82.9.
Yeah.
All right, you're going to have to make me calculate that. You guys be careful in your calculations now.
Mm-hmm.
So,
I just want to make sure I'm doing it right.
I want to make sure you're doing it right. And you know you can use Google for this if you just type it right in. 19,900 divided by 240. That would be 82.9. Thank you very much.
83 then?
No, go ahead. If you've got it to the 10th, leave it at the 10th. We want this ratio as close as possible because we're going to be doing some further calculations. So let me get my eraser out.
Yeah, my calculator was in the wrong mode.
That's okay.
Calculator, my son stuck it.
82.9. And you know, this is on a level of importance, probably a 10, 10 being the most important. I'm sure you guys know what a foot is, 12 inches or whatnot. This is something that's, I'm sure, if not practically new, brand new to you, is that number has got have to be pretty, it's going to have to be right. Double check your work. If you come down here and you say, am I sure it's 82.9? Just multiply it by 240 and you should get this number up top. If it doesn't calculate out correctly, then you've done something wrong. So double check your work when you're doing these. Professor B and I have seen plenty of students where they've, just keyed it in wrong in a calculator, and it really has hosed up their answer. I'm kind of a techno guy. I do teach computer stuff too for some students on the side. You can actually just talk into Google Voice or even talking to Alexa, what's 19,900 divided by 240, and you're going to get that answer. So you use those resources. I've got no problem with it.
It can't be less than it, can it?
All right, let me cancel that. Can this be less than what?
Because I did 82.9 times 240, and it was like 19,860 something.
That's close enough for work right there. We're not going all the way out. If you go to the 10th on that number right there, I'm fine with it.
All right.
All right.
That couple numbers off, it's still right.
Correct. And you'll see later, I'll do one example, even though I don't want to get that far today. What time is it? 10:56. I don't want to overload you guys too much. I do want you to know how to figure this out, but we'll show one example of how this works as far as doing other values into the transformer. All right, let's do another one. Transformer.
Sent you a message there, Professor.
Yes, sir.
Okay.
Where is it at?
Sent to you on the
Zoom?
chat.
It's in Zoom?
Yeah.
Hold on. I'm going to share, so I don't have to go. Okay, no problem.
Good.
Thank you for letting me know. Yeah, I forgot you're back down there in God's country. All right, so let's take another one. Input voltage, 2400 V. This is going to be simple. Output voltage, 240 V. Ratio?
Probably 1 to 100.
Easy.
1 to 10.
1 to 10.
Yeah,
10 times 240 is 2400. So 1 to 10. All right, one more. I'll give you something a little bit more difficult. All right, 4800 V. Here's my transformer. Output voltage, 277 V.
17.3.
So your solution was 17.3. Where does that number go? Top or bottom?
Bottom.
Bottom. If we want to check our work, we're going to take 17.3 and multiply it by 277. That should give us something that's very close to 4,800 volts. And our 1 comes up in this area. So 1 to 17.3. All right. For our next quiz, we're going to give some of these do know how to do these. Is computing ratios on transformers when you have a primary. And what do we as professors need to provide? We're going to need to give you a primary voltage and a secondary voltage. You need to compute the ratio between the top voltage and the bottom voltage and tell me what it is. Now, who's my mathematicians out there in the world? Quantum physics, trigonometry, all that good stuff. In true honesty, guys, out there in the world, when you're using ratios, they should be two whole numbers. Are we creating two whole numbers here?
No, sir.
No, we're creating a whole number and a fraction down here at the bottom. For our purposes to do computations on voltages, it's okay. All right, don't get all freaked out that you got, this is actually, 17.3 is actually another ratio when you think about it, but that's okay. When I'm figuring this ratio right here, I need this number as close as possible, and we're going to the 10th to be able to do computations on something else. I will do one of those just to show you how it works. You're not going to need to know it for the next test or quiz, but it'll give you an idea of the direction we're heading. Transformer. And eventually, we'll do this so many times, you're going to learn these things by heart. 7,200 volts in, 240 volts out. What's my ratio?
30.
1 to 30. Okay. Thus far, we've talked about what unit of measure in electricity?
Volts.
Volts. Okay. I'm going to introduce something new. There are 3 amps flowing through this conductor into the transformer. How many amps are coming out of the secondary side of the transformer?
Would it be 90?
Exactly. 1 to 30 is my ratio. You need to figure that first. Now I've given you a new number concerning amperage. If you're going down in your calculation, 3 times 30 equals 90 amps on the secondary side. All right, watch this. $7,200. 240V. 240. What's my ratio?
1 to 30.
Thank you. I'm going to take a measurement down here, and I have 120 amps of current flow. How much is my current flow on the primary side?
4 amps.
How'd you do it?
Divided it by 30.
There you go. I took my 120, divided it by 30, which gave me 4. So when I did my when I had my number here, and I calculated down, I multiplied. When I have my number here, and I'm trying to figure the number at the top, primary side, I divide. No matter what the numbers are, that's the course I take, okay? Upper number available, multiply. Lower number available, divide, okay? That's just a precursor of things to come in the future. You won't need to know that in the next test, but I did want to pass it on as to the direction we're heading to find out how we can compute different values when we're only provided with 2. All right, any questions there? Hearing none. Gentlemen, we will see you at the yard this afternoon. Same thing as yesterday. We're going to try to get back in the mode of pulling poles. I had to leave for a meeting yesterday. Does anybody know how many more poles got pulled?
I think total of 8.
Eight are pulled.
They finished the second row.
They finished the second row, so we'll get back on that other row. And the plan is to go ahead and get all those poles pulled out, drag them off to the side like we did earlier. We're going to take that line truck and probably that mini excavator and start dragging new poles to the holes where they need to go. Bring over material, start framing those up, and then we'll take the auger on the line truck, clean the hole out, and reset new poles. Plenty of work to do out there. Plus 2, I mean, if you want to work with the line truck or on the line truck for a little bit, that's fine. If you want to go climbing for a little bit, just rotate around and get some climbing in. I saw plenty of people climbing up to the top of that 50 yesterday, which is fantastic. Your form looks a little bit like it needs some work, but there will be a day that's going to come where all of you are going to be tasked to climb to the top of a 40-foot pole just to make sure that everybody's square and good with the heights. So anybody got any other further questions for this morning, and what's on tap for this afternoon? Again, the quiz is available till midnight tonight. I've got no problem that if you guys that are driving and working or whatever you need to do, if you jump out there at the field and it's 12:30 and you want to get on your phones, laptops, whatever, and knock that quiz out and then come out there with us and do your work, that's fine, just as long as it gets done today. Dalton. Dalton Jefferson. And he needs to turn that video off. That's getting kind of weird. Okay, any other questions today, gentlemen?
No, sir.
All right, let's shut it down. We'll see you at the field at 12:30.